Dr. Rico here. This is a lecture from my mini course, Robotic Planning and Kinematics. The syllabus and notes are in the description. Welcome to Lecture 9.2, Linear and Angular Velocities, part of the Linear and Angular Velocities of a Rigid Body chapter. So, we now consider bodies that are not only rotating, but also translating. In other words, the origin of the body fixed frame that moves with the body, sigma 1, is moving with respect to the fixed inertial frame, sigma 0. In what follows, we drop the time argument for simplicity of notation. Lemma 10.5, Linear and Angular Velocity. Recall that we represent the location and orientation of sigma 1, the reference frame sigma 1, with respect to sigma 0 by the displacement matrix H10, which includes as a submatrix the rotation matrix R10 and the translation of the origin transformation O10. This is the homogeneous representation of this rotation and translation together called a displacement. Recall the notions of angular velocity in inertial and body frames, omega 010, which means the reference frame angular velocity of reference frame 1 with respect to reference frame 0, written in the 0 reference frame, and omega 011, which is again the 1 reference frame written with respect to the 0 reference frame, expressed in now the 1 reference frame. Define the linear velocity of the body frame origin by O10 dot, which is the time derivative of the translation 1 with respect to reference frame 0. With these premises, we write the body velocity as a 4x4 matrix, homogeneous form, again, H10 dot, so the time derivative of the H10 transformation. Okay, so the time derivative of H10 is H10 multiplied by this matrix on the left-hand side here. And this matrix has within it a skew-symmetric matrix, that's this hat operator, that is constructed via the angular velocity of reference frame 1 with respect to reference frame 0, written in the 0 reference frame. V10, which is, as we'll see below here, the relationship of the displacements, in fact, the velocities, the translation velocity. So the origin transformation is inside this V10. So that's 9.3. So V10, this translation component, is O10 dot minus omega 010 cross O10. So that's the velocity of 1 with respect to 0. Similarly, in the body frame, we have H10 dot equals H10. Now it's right multiplied by a similar matrix. This time the matrix uses omega 011, so the angular velocity expressed in the 1 reference frame, and V11, V1 expressed in the 1 reference frame, where V11 is R10, O10 dot. Little proof. It is a simple calculation to compute H10 dot times H10 inverse and show that the equalities 9.3 and 9.4 hold true. So this isn't really a derivation, it's just a proof that they work. Just plug them into that expression and see that these two equalities hold. Finally, it is interesting to consider a point P attached to body frame sigma 1 so that P1 dot, the time derivative of P1, is 0, and compute the homogeneous representation of P in the 0 reference frame, the time derivative of that, which is equal to H10 dot P1, and we can expand upon this using the identity that we found earlier. We can either use the left multiplying matrix or the right multiplying matrix. We chose to use the left multiplying matrix in this example, and that's where h10 dot was replaced with. And we're left with this relationship here. So the time derivative of p0 is p0 left multiplied by this matrix. So if you were to figure out what the non-homogeneous representation of p0 is, we would have that the time derivative of p0 is this term, which you can essentially read off the first three rows of the expression in 9.5, and you can also rewrite this as shown. This relationship is the velocity equation for a point fixed with the body and generalizes equation 9.2, which was right here at the end of the previous section, where we find the time derivative of p0. Okay, good. Basic velocities. Recall that we defined the three basic rotations in section 6.3.4 and the six basic displacements in section 8.2.1. We are now in a position, if you will, to present the basic independent velocities of a rigid body. First, let us consider the rotation of a rigid body and neglect its position. So we're just going to focus on its rotation. For a time-varying rotation matrix, the set of angular velocities in either inertial or body frame is the set of skew-symmetric matrices SO3. Second, from the results in Lemma 9.5, we know that the set of linear and angular velocities of a rigid body is given by the following set of matrices. So the special Euclidean group, SE3, where we have matrices of this form, where S is one of the special orthogonal group members and V is a vector in R3. Accordingly, there are six basic velocity vectors, just like the six basic displacements, the infinitesimal rotations about the three axes, and the infinitesimal translations along the three axes. Next, it is convenient to introduce the operation, the hat operation, here with a map from R6. So we take a vector in R6, we map it to the special Euclidean group of displacement matrices. And what we're taking there are the angular velocities about x, about y, about z, and the translational velocities, vx, vy, and vz. And we are taking that hat operator to mean construct from these components this matrix. Okay. With this notation, the six basic velocities are then the basis vectors E1 hat through E6 hat, where E1 is 1 and then everything else 0. E2 is the second term is 1 and everything else is 0, etc. down to E6. These are the basic velocities expressed with these time derivatives of displacement matrices. All right, that's all I've got for you for this, and I'll see you in the next section. Take care.